Yo, what's up, everyone? Welcome to Oxidation Reduction Part 3. Today, we're going to be talking about electrolysis. Let's talk about what is electrolysis. Remember, in a galvanic cell, chemical reactions are used to produce electricity. In an electrolytic cell, electricity is used to cause chemical change. Electrolysis is simply using electricity to drive a non-spontaneous reaction. For example, you might have something like this where you're turning water back into hydrogen and oxygen gas, and the apparatus would look something like this. And then over time, what you'll realize is that gas evolution happens, and then you have that hydrogen gas and you have that oxygen gas. We're going to go really in depth into how this apparatus works, so don't worry if you don't understand it right away. Okay, so let's get a bit more in depth into these electrolytic cells. Oftentimes, electrolytic cells are not separated by they're usually not separated, so a salt bridge is quite optional in some of these. You'll see that really there's no need to charge balance these out because they kind of charge balance on their own. Um, but other than that, they're still gonna need those two electrodes that you have in galvanic cells. So there are these two electrodes, and they're usually made of inert metals like graphite or iridium or platinum. And the point of just these electrodes is to transfer electrons from one electrode to the other electrode without having any effect on the reaction itself. Okay, so now what we have now is just two electrodes in an electrolytic cell. Now, these guys aren't going to do anything unless we put an electric current through them. An electric current goes through the two electrodes in order to produce an, oh whoops, this should say anode and a cathode. And so which is going to be which? Well, so which one is going to be which, right? Well, since negative charge is flowing to this electrode right here, this is going to have a negative charge, and this one is going to have a positive charge. Now, you might notice that something is wrong with this. By the way, this just represents like a battery here. This is like the symbol for a battery. And so the negative current is flowing that way, and the positive current is flowing that way. What's really happening is that electrons are flowing from one electrode to another electrode. So what this electric current is doing here is that it's taking electrons from the electrode here and transferring it to this electrode over here. It's going in a cycle, and that's what this battery that's what this symbol here represents. This is a battery. And so that battery is necessary for this transfer of electrons. So since electrons are flowing from this electrode to this electrode, well, this electrode is going to have a negative charge, and this electrode is going to have a positive charge. Now, there's a little problem with this, and if you're familiar with like electricity, then you'll notice what the problem is. The problem is that the circuit is not closed. So whenever you have a flow of electricity, you always need the circuit to close. And you'll notice here that the circuit doesn't really close. This part here is completely missing. And so how do we get the flow of electrons from this part to that part? Well, what we do is that we put an electrolyte solution. The electrolyte solution is necessary for the flow of electrons. So electrons can't flow through water. Water is a very good insulator. But on the other hand, if you add an electrolyte solution, you allow the flow of electrons. And we need that in order to close the circuit. And so truly now, electrons flow from the positive side to the negative side. And the positive side is what we call the anode, and the negative side is what we call the cathode. And remember, this is just because oxidation is happening at this electrode. Sorry, oxidation is happening at this electrode, and reduction is happening at this electrode. Now that the circuit is closed, we're going to see some interesting things start to happen. First of all, the electrodes and the cathodes are going to start attracting their opposite charges. So what do I mean? Well, you realize that the anode here has a positive charge, but the cathode here has a negative charge. And remember, negative attracts to positive and positive attracts to negative. So what's going to happen is that cations are going to flow to the negative terminal and anions are going to flow to the positive terminal. And it's going to look something like this. So the sodiums are going to be attracted to the cathode and the OHs are going to be attracted to the anode. Now you might notice that OH has an excess electron. The anode is going to pull on that electron. So what's going to happen is that the electron gets pulled out and it starts moving. So excess electrons from the OH flow from the anode to the cathode. And remember, this is happening because of that electrical current. Without an electrical current, this would never happen. Now, what happens to the OH after the electron is lost is exemplified in this equation here. So at the anode, 4 OHs are going to get turned into water, oxygen gas, and 4 electrons. So really, all these OHs are gone. What's going to be replaced is 2 water molecules, so H2O, H2O, and you'll see some gas evolution of O2. At that point, they're all gone. Now, you might expect at the cathode for a reaction like this to happen. So the sodium gets the electron and it turns to just solid sodium. The problem with that is that its cell potential is really, really high. It's negative 2.71, and or rather, it's really, really low. Um, the cell wants to do the reaction that has the highest electrochemical potential. Another reaction that it could do is it could take the water and just give the electron to the water. And you'll notice what happens is that it turns to hydrogen gas, sorry, hydrogen gas and 2 OHs. And the cell potential of this is negative 0.83. You can see that's a lot higher than the cell potential of the sodium, and therefore this reaction occurs a lot more frequently. So what you'll see happen is that the sodiums are replaced with the water, and then afterwards the electrons are going to flow into the water. And at that point they're all just going to, get used up, and then we're going to have H2 gas and we're going to have 2 OH minus ions. And those 2 OH minus ions are just going to flow to the anode and get used up in the anode reaction that we have over here. So really it's this cycle. Similarly, in the anode, you realize water is being produced, so that water is going to be used up in the cathode to produce more hydrogen gas. So the overall reaction for this would look something like this. So water is going to turn into oxygen and hydrogen gas. And you can see the E cell of this is negative 1.23 volts. Remember, all this is happening in an electrolytic cell. So this would never happen naturally unless you applied a current to it. And the amount of current that you need is 1.23 volts or higher. This E cell value tells you how many volts you need to apply to this system in order to get this reaction to occur. If we take a general picture of this, it will look something like this. And you'll notice one thing different here, and it's that we have these tubes around it. And those tubes are only so that we can collect the gas, and the gas just doesn't, flow out to the atmosphere. And so what would happen over time, you'll notice, is that you would have twice as much hydrogen as you do oxygen. And from the chemical equation, you can see why that is, because we're producing 2 hydrogen gas as opposed to 1 oxygen gas per reaction. Now, I found this really cool video of someone doing the experiment, and it was really simple. And the beauty of it was that it's really simple, and I want to show it to you guys. I don't think it's going to allow me to play the video here, but I'll just edit it on so you guys can see it. Essentially, they take this battery, and they make a really, really simple setup. And you can see how fast the the gas evolution starts to happen. It starts bubbling up, and those bubbles are those hydrogen gas and oxygen gas. This electrolytic process here was one of the first ways that people realized that, water and oxygen hydrogen and oxygen are in a 2-to-1 ratio in the water molecule, because you produce twice as much hydrogen as you do oxygen. Okay, let's do a bit of practice from the test. So electrolysis of water containing sulfuric acid as an electrolyte is carried out. By the way, the electrolyte that we used in our experiment was NaOH. But usually you can use a bunch of other electrolytes. You just need electrons to be able to flow from the anode to the cathode. Or sorry, from the cathode to the anode. You just need the circuit to be closed. So let's keep reading. Carried out as shown, and the gases produced at the electrodes are collected in two identical tubes, both initially filled with sulfuric acid solution. After electrolysis has been carried out for a certain time, which picture best represents the appearance of the tubes? Remember, since we're doing the electrolysis of water, one of the tubes is going to have double the gas concentration of the other. So you can see in A, one tube has collected a bunch of gas and one tube has collected no gas. Now, that would not be realistic because what we're producing is hydrogen gas and oxygen gas. And these are both gases, so they would all evolve to the top. B makes sense. B has you can see that the one of them has doubled the volume of another. So the gas volume of the one on the left would be the one for the hydrogen, and the one on the right would be the one for the oxygen. So B totally makes sense. Let's just leave it there. C doesn't really make sense. You're not producing the same amount of gas in each container because you're producing twice as much hydrogen as you are oxygen. So this wouldn't make sense either. Now, D might look really tempting because you can see that the volume on one half is half the volume of the other half. So that would kind of make sense because, again, there's double as much hydrogen produced as oxygen. But the problem with this is that it kind of mixes it up. So at the positive end, remember at the positive end, we're going to be producing the oxygen. And at the negative end, we are going to be producing the hydrogen. Let's go back to our diagram here. At the anode we produce the oxygen, and at the cathode we produce the hydrogen. Um, and what this diagram here does is that it flips it. So essentially what it's saying is that over here would be the oxygen, and over here would be the hydrogen, which doesn't make sense because in this case we're producing double as much oxygen as we are hydrogen, and that wouldn't make sense. And so D cannot be right. Therefore, the only answer here that makes sense. Oh, whoops! I think I put up the answer. The only answer here that makes sense is B. And as you can see, we are correct. So again, make sure you have the right concentrations of hydrogen and oxygen respectively, and make sure that they are being produced at the right electrodes. So that's all I have for electrolysis. Make sure that you remember how electrolysis works. Remember how the electrodes get a charge, and so the ions move to those electrodes, and then the electrons flow from one electrode back to the other electrode, and certain chemical reactions occur at those electrodes that allow electrolysis to happen. That's all I have. I hope you learned something, and I hope to see you next video. Thank you for watching.